Hi everyone. So I'm just going to work through the other example calculations, the other example problems that I didn't get a chance to run through during lecture today. So here is one, and again, this one is quite similar to one we did run through class. So on the one hand, it will be similar, so you can recap it, and it's different enough that you get to do something different. So let's say you mix 1 liter of hydrofluoric acid with 100 milliliters of sodium hydroxide of strong base. And you'd like to know what is the pH of the resulting solution. So standard way we do this, as always, is we ask, okay, what are the major species dissolved in solution? Let's make sure we can just describe our chemical system and know what is in it. Well, we know we'll have hydrofluoric acid that was dissolved. We know we'll have sodium hydroxide. You could also argue that since sodium hydroxide is a strong base, it immediately dissociates into sodium plus and hydroxide ions. And since this is occurring in an aqueous solution, we also have a bunch of water molecules present. So next step is saying, okay, what reactions go to completion? Well, I've already mentioned one of them, that sodium hydroxide converts into sodium plus and hydroxide. Oh, I keep making this mistake. That should be 1 molar sodium hydroxide. 100 mils of 1 molar sodium hydroxide. So I know if I start with 0.1 moles of sodium hydroxide, it's going to immediately convert, it's going to react to completion and give me 0.1 moles of sodium ions and 0.1 moles of hydroxide ions. So that reaction goes to completion. So I have 0.100 moles of hydroxide ions. Are there any other reactions that go to completion? And there is. Because I have a weak base present, I have hydrofluoric acid present, and since I've added sodium hydroxide, I have hydroxide ions which act as strong bases. I have a reaction between a strong base and the weak acid, hydrofluoric acid. So if I start with 0.1 moles, so I'm sorry, I should complete the reaction. What happens here is the hydrofluoric acid donates its proton to the base, so you get H2O and fluoride ions. So if I start with 0.1 moles and 1 mole of hydrofluoric acid, which is what I was starting with, it was supposed to be, I apologize, 1 liter and 1 molar. A 1 liter of a 1 molar solution of hydrofluoric acid should have 1 mole of hydrofluoric acid present. If I'm adding 100 mils, 1/10 of a liter of 1 molar hydroxide, I should have 0.1 moles of hydroxide ions. Those will react. I will lose all of my 0.1 moles. I will lose 0.1 moles of hydrofluoric acid, and I will produce 0.1 moles of the fluoride ions. And then what I'm left with after this reaction goes to completion is, I assume I have no hydroxide, 0.9 moles of HF and 0.1 moles of fluoride ions. So I'm going to copy all that up here. I know I have in solution 0.9 moles of hydrofluoric acid. I should have, originally here, I have 0.1 moles of sodium hydroxide. I now have basically no moles of hydroxide left over, and the rest of this is H2O. And I now also have an appreciable amount of fluoride ions present. those were generated by the addition of the strong base to the weak acid. Some of the weak acid, it donates its proton and becomes fluoride. So now these are the species that I have in solution, and those are the key quantities. So those are the reactions that go to completion. The next step is to think, okay, what are the equilibrium reactions that could occur? Well, there's the autoprotolysis of water, that's always going on. And the K for that is 10 to the negative 14. I also have hydrofluoric acid and fluoride present. So HF, for example, can react with water and produce fluoride ions and hydronium ions. The Ka for that reaction is about 10 to the negative 4. Okay, again, I would need to look that value up, and I did look that value up, and I obviously didn't give that to you initially, but if this were a real problem, I would give you the actual Ka for the fluoride ion, for HF. Technically, since fluoride is a weak base, this reaction is also possible. Fluoride can react with water and produce HF and hydroxide ions. The K for that reaction, the Kb of fluoride, is quite small. I'm going to give you a homework problem where you work through this derivation, but you can assert that the Ka of an acid times the Kb of its conjugate base is equal to Kw. Again, I'm going to give people a homework problem to work through this derivation, and essentially the derivation is also in your textbook, but I will just assert this to you at the moment, that if you have a weak acid, its conjugate base can behave as a base. The equilibrium constant for it behaving as a base, taking a proton from water, is related to the Ka of the original weak acid, and their product is equal to the autoionization constant. So this should be Kw over Ka. So this ends up being around 10 to the negative 10. So these are the different equilibria to consider. The dominant equilibrium is whichever one has the largest equilibrium constant. That's the one that is going to be going most strongly towards its products. That's the one that wins out. Everything else is sort of slave to it. So that means this is the key equilibrium that we're going to concern ourselves with. And solving this equilibrium problem will tell us the hydronium concentration. And once we have the hydronium concentration, we can get the pH. So let's do that. So I'm going to move this up here. So I have I'll do an icebox here. So my initial hydrofluoric acid concentration should be 0.9 moles over 1.1 liters. Again, I've added together these two volumes, and your icebox calculation should always be in terms of concentrations because you're going to end up sticking them into an equilibrium constant expression, and the law of mass action equilibrium expressions are expressed in terms of concentration. So we need to convert this to a concentration. We don't worry about water, it's a liquid. The hydronium concentration we're going to assume is quite small. Before this dissociates, all we had in solution was water, regular plain old water, which is not going to produce much hydronium. And I'm also starting with 0.1 moles of fluoride in 1.1 liters. So we expect, okay, we are missing one of my products, so my reaction should shift right towards the products. So I should lose some HF, generate some hydronium, and also generate some fluoride ions. So 0.9 over 1.1 is about 0.818 minus x, and then 0.1 divided by 1.1 is about 0.091 plus x. So these are my equilibrium concentrations. And then I can plug that into an equilibrium expression. Should be concentration of hydronium times concentration of the fluoride ion over the concentration of HF. I have these concentrations, so I get that this should be x times 0.091 plus x times 0.818 minus x. So, how do you solve this? At this point, this is an algebraic equation. We know the Ka value. I had it written here previously. I'll remind you again, its specific value is 6.6 times 10 to the negative 4. I want to solve for x, and by solving for x, I get the hydronium concentration, then I get the pH. So there's some, if you completely multiply this equation out, you can solve it. You can solve it using the quadratic equation. I am going to make a few approximations here. I will approximate that, say, okay, yet again, I expect x to be quite small. So 0.818 minus something small, I'll assume that that's also around 0.818. And similarly, 0.091 plus something small, I'll assume is pretty close to something small. Or rather, it's pretty close to 0.091. So I will assume that this ends up being approximately equal to 0.091 divided by 0.818 should be equal to Ka, and then I can say x should be equal to Ka times 0.818 over 0.091, and then I predict that x here should be about 0.00593. The exact value ends up being about, if you don't make that approximation, the exact value is 0.00555. So you are off by a few percentage points, but it's a reasonable amount. It's a reasonable error, and we'll just kind of accept it. And then once you get this, you can plug this into the pH equation. We know pH is negative log of the hydronium concentration. And I just realized as I'm looking at my notes, I use the exact value. Let's use our approximate value and get this. So that should be negative log of 0.00593, and that ends up being 2.23 is the pH of this solution. All right, so that's one example, and admittedly an involved example, because we needed to take into account that there's a reaction that occurred first. We needed to do the stoichiometry of that, and then we also needed to work through a full equilibrium calculation because there was some equilibrium reaction that was setting the pH. Okay, so let me try two more here. I'm sorry, one of these I actually did manage to work my way through in the 9 a.m. class, but the 8 a.m. class didn't see it, so I will work through it as well. So this one is saying, suppose you have a 1 molar solution of ammonia. Just a 1 molar solution of ammonia, which is a weak base. Actually, actually, let me get the value of that. 1.8. And I would say what I might want to know, what is the pH of this solution? So standard analysis, major species present in solution. Well, it's an aqueous solution, so there will definitely be water. There will be ammonia present, certainly. And that's it in terms of major species. Any reactions that can occur? Essentially, no, there are no reactions here that go to completion, so we don't have to concern ourselves with that. The third part here is to consider the major or the dominant equilibrium. So there are two here. As always, we have the autoprotolysis of water. For which the K is 10 to the negative 14. And we also have the action of ammonia as a base. It reacts with water, takes a proton from water, and becomes ammonium and hydroxide ions. And again, the equilibrium constant for this, K, is 1.8 times 10 to the negative 5. So it's about, 10 to the negative 5. So it's about 1 billion times larger than the K for the first reaction, meaning that this will be the dominant equilibrium. It's the one that goes most forward. This reaction will set or determine the concentration of hydroxide. And then later we can figure out the concentration of hydronium because that is determined by this equilibrium reaction. What we'll do is we'll figure out the hydroxide concentration, and then once we know the hydroxide concentration, I can say, well, Kw should be equal to the hydronium concentration times the hydroxide concentration. If I know this from my ammonium equilibrium, if I know this, and I know Kw, then I can solve for hydronium, and if I know hydronium, I can get the pH. So that's what we're going to do. So let me solve this equilibrium reaction here for ammonium. I guess I'll just work with this. So I should have my initial change, and what I have at equilibrium, I assume that I have 1 molar ammonia. Water doesn't factor in, and we can assume that we have no ammonium and no hydroxide ions present because they haven't dissociated yet, and it's just in water, so there's no major source for hydroxide ions other than this reaction. So there's no products, so I should shift right and produce some products. So I have 1 minus x, x, and x. So what I have here then is that Kb, my equilibrium expression, should be equal to the concentration of ammonium times hydroxide over the concentration of ammonia. And then I can plug in my equilibrium concentration, so I got x times x over 1 minus x. So x squared over 1 minus x should be equal to Kb, which again is equal to 1.8 times 10 to the negative 5. If I make the same approximation we've been making previously, I would probably assume x would be small, and so this should be approximately equal to x over 1. 1 minus something small is approximately equal to 1, so that should be equal to Kb. So if I multiply over the 1 and I take the square root here, I should have that x is equal to the square root of Kb, which is 1.8 times 10 to the negative 5. So that is about 0.00424. That is the value of X, which is also my hydronium concentration. So now this value is known. I can calculate hydronium concentration using my knowledge of the autoprotolysis of water. So I have here that hydronium should be Kw over hydroxide. So that's 10 to the negative 14 over 0.00424. That value is 2.36 times 10 to the negative 12. And then if I take the negative log of that, I end up with a value of 11.63. And that's a reasonable value for the pH. I have a solution of a base, of a weak base, and bases, if they are basic, their pH should be greater than 7, which is exactly what we see, so that makes sense with our intuition. Okay, one more example calculation here. Let's say I have a solution a 1 molar solution of sodium fluoride. And I'd like to know what is that solution's pH. So standard analysis here. I know that the major species this substance is an ionic compound. If it's soluble in water, it should dissociate into its constituent ions. So that should be sodium plus. Those will be present in solution. I should have fluoride ions, and I should have water present. Are there any reactions that go to completion? Well, other than the dissociation of sodium fluoride into sodium plus and fluoride minus, there are no other reactions here that go all the way to products. There is, however, one other reaction, one other so I need to decide what are the equilibrium reactions to consider. There's two of them, as always. There's the autoprotolysis of water. And there's the interaction of the fluoride ion with water. It has the ability to act as a base because it is the conjugate base of hydrofluoric acid. It takes a proton, becomes HF, and produces hydroxide ions. Oh, I'm sorry, originally the question here was, if I have this solution, what is the pH? So this reaction, its equilibrium constant, the Kb of the fluoride, that should be equal to, I worked through this, I presented this just a second ago, it should be the equilibrium, the autoionization constant divided by the Ka of hydrofluoric acid. So that value ends up being about 1.52 times 10 to the negative 11. So between this reaction and this reaction, this is the dominant equilibrium reaction. It goes most forward, and it will set the hydroxide concentration. So I can solve this equilibrium problem with an equilibrium system with an icebox calculation, get the hydroxide ion concentration, and once I know the hydroxide ion concentration, that will set up the hydroxide concentration and the hydronium concentration that I'm getting from the autoionization of water. So it's going to be somewhat similar to what we did with the analysis for a weak base, the one I just worked on, because yet again, it's a weak base that's setting the hydroxide concentration, and in turn, the autoionization of water sets the hydronium concentration in terms of the hydroxide concentration. So let me solve this very quickly here. It's going to be a very similar calculation to ones we've already seen. Because again, it will be another icebox. So I know that I have fluoride reacting with water to make HF and hydroxide. I assume initially I have 1 molar HF. Water doesn't factor into the equilibrium expression. I assume that there is initially no HF present and no hydroxide ions present because they haven't dissociated yet. There's no other source for hydroxide ions. I will shift right and produce products since I initially have no products. I'll leave the KB there for the time being. So my equilibrium concentrations are 1 minus X, X, and X. So if I want to plug these values into my law of mass action, that should be HF times hydroxide ion over the fluoride ion concentration. So that should be X times X divided by 1 minus X is going to be equal to KB. Because KB is very small, we expect X to be small. We don't expect the reaction to go very far to products. So this should be approximately equal to X squared over 1. Move over the 1, and then take the square root. So I get that X is equal to the square root of KB. KB again was originally was 1.52 times 10 to the negative 11. That square root is going to be 3.9 times 10 to the negative 6. And that again is my hydroxide ion concentration. The question is, what's the pH? To get the pH, we will need to know the hydronium concentration. And as I just argued, the hydronium concentration is determined in turn by the hydroxide concentration because the autoionization of water tells us that they should be inversely proportional to each other. So I can solve for hydronium concentration. So that ends up being 10 to the negative 14 divided by 3.9 times 10 to the negative 6. That ends up being, oh goodness, I just plugged that directly into the calculator and I didn't write it down. So let me calculate that. That ends up being 1 negative 14 divided by 0.9 negative 6. So that ends up being 2.56 times 10 to the negative 9. If I plug that in, wait a minute, that doesn't make any sense. Does that make any sense? Oh, wait a minute. Give me 1 second here. Times 10 to the negative 6. Okay, I guess I must have made an error in my own calculations. So that should be 2.5 times 10 to the negative 6. So you have negative log times of the hydronium concentration. So that's 2.56 times 10 to the negative 9. That ends up being 8.59, which is slightly basic. Which again is something that we sort of asserted in passing, or we asserted on Monday, that if I had this solution of sodium fluoride, I asserted at the time that it would be basic because it contains the fluoride ion. the fluoride ion is the conjugate base of HF, and as a result, it can act as a base in solution and give you a basic solution. Okay, so those were a few examples that I have prepared. If you have further questions or you'd like to work through more examples, I will be very happy to work through them with you. That is it for today, for this lecture. If you have any questions, I will be happy to answer them. Have a good day.